The entire universe, everything you see and touch, from the smallest atom to the most colossal galaxy.
Yeah.
It's all built from just a handful of fundamental building blocks and governed by just a few universal forces.
It's like the ultimate Lego set, isn't it? And our best blueprint for that, our deepest understanding, is the standard model of particle physics.
Exactly, and that's where we're plunging today. Our mission is to unpack this incredibly intricate model, but with a specific focus on some surprising players, composite particles called mesons. We want to get into the what, how, and why of these tiny messengers.
And specifically their role, which is kind of unexpected, in two fundamental forces, the strong and weak interactions.
So where are we drawing this from today?
Well, we're basing this on a really solid introduction to the standard model, plus some more recent discussions that really highlight how mesons fit into the picture of fundamental forces. It connects some interesting dots.
Okay, great. So let's start with the big picture. The standard model itself. What is it, fundamentally?
Right. Think of it as the main mathematical theory we have. It describes the weak, electromagnetic, and strong interactions, and it describes them acting between the fundamental particles, leptons, and quarks. It's basically the rule book for all the stuff in the universe, how the elementary bits, the fermions, interact through fields.
And these fields have particles associated with them, the force carriers.
Exactly. Those are the bosons. They're the messengers, the mediators of the interactions.
Okay, so let's take the electromagnetic one first. That's photons, right?
Photons, yeah. Massless spin-1 particles. They carry the force between anything with electric charge.
And because they're massless, the range is infinite.
Infinite range. That's why we can see distant stars, why electricity works the way it does. It's a long-range force.
Okay, then what about the weak interaction? That one sounds a bit more mysterious.
It is, in a way. It's mediated by the W plus LeVu-W and the neutral Z bosons. Big discovery back at CERN in '83. And the key thing here, unlike photons, is that these guys have mass. A lot of mass.
How much mass are we talking?
Well, the W is around 80 GeV. The Z is about 90. That's like 80 or 90 times heavier than a proton. Really hefty.
Wow. And that mass has a big consequence, doesn't it?
Huge consequence. It makes the weak interaction incredibly short-ranged. We're talking about 10 to the minus 3 femtometers. Tiny.
So it only really acts inside atomic nuclei, that sort of scale.
Well, exactly. A stark contrast to electromagnetism's infinite reach.
Okay, and the strong interaction, what carries that?
That's gluons. Like photons, they're massless, spin-1 particles. Their main job is, well, gluing quarks together inside particles like protons and neutrons. We'll get more into that.
Got it. And one quick note, gravity isn't in the standard model, is it?
No, it's explicitly left out, not because it isn't fundamental, but at the tiny scales particle physics deals with, gravity is just incredibly weak compared to the other three. It's negligible in these interactions.
That makes sense. All right, so those are the forces. What about the building blocks themselves? The matter particles.
The fermions, right. Two main families. First, you've got the leptons.
Like the electron.
Exactly. The electron, the muon, the tau. Those are the charged leptons. And then each has a corresponding neutrino, which are almost massless and very elusive.
And the Dirac equation predicted antimatter for these, like the positron.
It did, yeah. A major success of early quantum theory. Every fermion has an antiparticle.
Okay, leptons and the other family.
Quarks. These are the really interesting ones for the strong force. There are 6 types, or flavors. Up, down, strange, charm, bottom, and top.
And they have electric charge like leptons.
They do, but they also carry a different kind of charge, which we call color. This is the charge associated with the strong interaction.
Color charge, not like actual colors, right?
No, it's just a name for the quantum property. Think of it like positive and negative for electric charge, but for the strong force, there are 3 colors and 3 anticolors.
And you said quarks are confined. You can't find one on its own.
That's right. They're always bound together inside larger particles called hadrons. This is because the strong force gets stronger as you try to pull them apart. It's a really weird property.
So they're permanently stuck together. What's the theory behind all this? You mentioned gauge theory.
Yeah, the standard model is a type of theory called a gauge theory. Quantum electrodynamics, the theory of light and electrons, is another example. It's built on this principle of local gauge symmetry.
Which means?
Basically, it ensures the laws of physics work the same way everywhere, regardless of certain changes in the fields. It dictates the form of the interactions. It's a deep mathematical principle.
Okay. And you also mentioned renormalization. Sounds complicated.
It is, mathematically, but the idea is crucial. When you first try to calculate things in these theories, you often run into infinities. which isn't helpful.
Doesn't sound useful now.
Renormalization is a set of techniques that sort of tames these infinities. It lets us extract finite, meaningful predictions about physical quantities that we can actually go out and measure. Without it, the standard model wouldn't be predictive.
Got it. So it's a mathematical toolkit that makes the theory work in practice.
Pretty much, yeah.
Okay, so that's the standard model in broad strokes. Now let's bring in the stars of today's deep dive. Mesons. What exactly are they?
Right, mesons. So they're subatomic particles, but unlike quarks and leptons, they aren't fundamental. They're composite.
They have smaller pieces.
Exactly. They're made of one quark and one antiquark, bound together by the strong force. They belong to that hadron family, like protons and neutrons, but they have a key difference. They behave like bosons.
Ah, so they can act like force carriers.
In a sense, yes. Their bosonic nature is important.
And they have quite a history, don't they? Something about Yukawa.
Oh, absolutely. A fantastic story. Back in 1934, Hideki Yukawa was puzzling over atomic nuclei. Why don't protons, all being positively charged, just repel each other and blow the nucleus apart?
Yeah, good question. Electromagnetism should push them apart.
Exactly. So Yukawa proposed there must be another, stronger force holding them together, the nuclear force. And he predicted a particle to carry this force. He calculated it should have an intermediate mass between an electron and a proton.
Hence Meson.
Hence Meson, from the Greek for intermediate. But then came a twist.
The muon.
The muon, yeah. Discovered in cosmic rays in 1936, its mass was kind of in the right ballpark, so everyone thought, aha, Yukawa's particle.
But it wasn't?
Nope. Turned out, over the next decade, that the muon barely interacts via the strong force at all. It behaves, much more like a heavy electron.
So it got reclassified as a lepton. The mu Meson name stuck around for a bit, though, causing confusion.
It did. The real Meson, the one that actually mediated the strong nuclear force, as Yukawa predicted, wasn't found until 1947.
And that was?
The pion, or pi Meson. That discovery finally confirmed Yukawa's idea, and he got the Nobel Prize for it in 1949.
A great example of how science sorts things out, even with detours. So what are mesons like? Are they stable?
No meson is truly stable. They all decay. But the lighter ones, like the pion, last longer, so they're easier to study.
And their masses vary a lot.
Hugely. The pion is light, about 135 psi, but then you have particles like the J-p psi, which is about 3 times the mass of a proton, or the upsilon, which is nearly 10 times, all quark-antiquark pairs.
Wow. And how do physicists keep track of them all? How are they classified?
It's based on several properties. Their quark content, obviously which quark and antiquark they're made of.
Yeah.
Also total angular momentum, spin.
Okay.
And then there are these quantum numbers called parities. P-parity, C-parity, G-parity. They relate to symmetries.
P-parity, that's left-right symmetry.
Yeah, and we know the weak force violates that. C-parity is about charge conjugation swapping particle and antiparticle, useful for neutral mesons.
Right.
And there's also isospin, which is useful for systems with up and down quarks because their masses are so similar. And of course, electric charge, determined by the quarks inside.
Lots of properties to juggle. Okay, let's dig into their roles. First, the strong interaction. You said gluons carried inside particles.
Right. Between quarks within a proton or neutron, it's gluons doing the work, exchanging color charge. That's the fundamental interaction described by QCD, quantum chromodynamics.
But the force between protons and neutrons in a nucleus, that's also the strong force, but it works differently.
It's more like a residual effect of that fundamental gluon interaction. And that force, the one binding nuclei together over slightly larger distances, is mediated by mesons.
Specifically pions.
Primarily pions, yeah. Think of it like this. The quarks and gluons inside the protons and neutrons are constantly interacting. Sometimes a quark-antiquark pair, a meson, can pop out, travel a short distance to a neighboring proton or neutron, and be absorbed.
So the meson acts like a messenger between the nucleons.
Exactly. But because mesons have mass, unlike gluons or photons, the range of this nuclear force is very short, basically confined to the nucleus.
So 2 levels of the strong force. Gluons inside, mesons between.
That's a good way to think about it, yeah. The meson exchange is an effective description of the force between composite particles like protons and neutrons.
And this is all part of QCD.
Yes. QCD is the gauge theory based on SU3, symmetry and color charge. It describes all these strong interactions.
They also have that weird property, asymptotic freedom.
Ah, yes. Fascinating stuff. Asymptotic freedom means the strong force gets weaker at very short distances or high energies.
So quarks inside a proton act almost like free particles if they're close enough.
Pretty much. But the flip side is that the force gets stronger as you try to pull them further apart.
Which leads to confinement, like a cosmic rubber band.
Exactly. You pull, and the force just gets stronger and stronger until it's easier to create a new quark-antiquark pair from the energy you put in, rather than isolating the original quark. That's why they're always confined in hadrons.
Mind-bending.
Okay.
Let's switch to the weak interaction. What's the main job of the weak force?
Flavor change. That's its unique role. The weak interaction is the only force that can change one type or flavor of quark into another, or one type of lepton into another.
Like in beta decay.
The classic example. A neutron has 2 down quarks and an up quark. It decays into a proton, which has 2 ups and a down. What happened?
A down quark changed into an up quark.
Precisely, via the weak interaction, emitting a W boson in the process, which then decays into an electron and an antineutrino. That's flavor change in action.
And since mesons are made of quarks, they must participate in this too.
Absolutely. Any particle containing quarks will feel the weak force and can undergo decays involving flavor change.
Can we walk through an example, maybe that K-son decay you mentioned?
Yeah.
K plus star.
The K plus meson is an up quark and an anti-strange antiquark. Now, strange quarks are heavier than up quarks, so it's unstable. How does it decay? Often into pions. It's a multi-step process involving both weak and strong forces.
Okay, break it down.
All right, roughly speaking. First, the anti-strange quark inside the kaon undergoes a weak interaction. It changes flavor.
Into what?
It transforms into an anti-up antiquark and spits out a W plus boson. That's the weak part.
Step 1. Weak decay of the antiquark.
Right. Step 2. That W plus boson is heavy and unstable, so it immediately decays. Also a weak interaction. It typically decays into, say, an anti-down quark and an up quark.
Okay, so now we have the original up quark, a new anti-up antiquark, a new anti-down quark, and another new up quark milling around.
Sort of, yeah. But now the strong force takes over to rearrange them into stable configurations. That new anti-down quark can pair up with the original up quark from the kaon.
Forming what?
Through the strong force, they bind together to form a pi plus meson, a pion.
One pion down. What about the others?
Well, the other up quark that came from the W plus decay might have too much energy. It can radiate some of that energy by emitting a gluon that's a strong interaction.
Okay.
That gluon carrying energy can then itself decay into a quark-antiquark pair, say a down quark and an anti-down quark. Again, strong force.
More quarks.
More quarks. Now, this new anti-down quark can join the up quark that emitted the gluon, forming another pi plus pion, strong force again.
2 pi plus mesons.
And finally, the down quark from the gluon decay can pair up with the anti-up antiquark from the very first weak decay step to form a pi meson. Strong force one more time.
Wow. So you start with 1K plus up anti-strange and end up with 2 pi plus mesons and 1 pi meson.
That's one very common decay path. Yes, it perfectly shows the interplay. Weak force initiates the flavor change. Strong force rearranges the resulting quarks into new mesons.
That is incredibly intricate. A little dance of forces and particles.
It really is. And remember, the pions themselves aren't stable either. They typically decay via the weak force too, often into a muon and a neutrino.
The weak force is busy. And this relates to that CP violation thing you mentioned. With kaons.
Exactly. Especially with neutral kaons. There are 2 types, K0 short, K0s, and K0 long, K0l, which are actually quantum mixtures of the kaon and its antiparticle. They decay differently, and studying their decays revealed that the weak force doesn't treat matter and antimatter perfectly symmetrically under mirror reflection.
That's CP violation.
That's CP violation. It's a tiny effect, but incredibly important. It might be the key to understanding why the universe is full of matter and not antimatter. Neutral kaons and also B mesons are crucial laboratories for studying this.
So mesons are key players in understanding some really fundamental asymmetries. Okay, let's zoom out again. How does this all fit into the bigger picture of unifying forces?
Well, a huge success of the Standard Model is electroweak unification. It combines electromagnetism and the weak force into a single framework.
Below a certain very high energy, they look different, but above it, they're unified.
Kinda, yeah. The theory describes them as different aspects of the same underlying electroweak force, and the key to how they appear different at lower energies is the Higgs mechanism.
Ah, the Higgs boson. That gives particles mass.
The Higgs field, yes, interacts with particles. This interaction gives mass to the W and Z bosons, making the weak force short range, while the photon remains massless, giving electromagnetism infinite range. It also gives mass to the quarks and charged leptons.
So the Higgs is crucial for explaining the differences we see. What about that renormalization thing and consistency?
Right, back to that. For the standard model, particularly the electroweak part, to be mathematically consistent and renormalizable, meaning we can calculate things without getting infinities, certain potential problems called anomalies have to cancel out.
Okay.
And it turns out, quite remarkably, that these anomalies do cancel perfectly, but only if the number of quark families exactly matches the number of lepton families.
So the fact that we have 3 generations of quarks, up, down, charm, strange, top, bottom, and 3 generations of leptons, electron, neutrino, muon, tau, neutrino, isn't an accident.
According to the standard model, it has to be that way for the theory to work. It suggests a really deep connection, a hidden symmetry between quarks and leptons.
That's beautiful, actually. But the standard model isn't the final word, right? There are still mysteries.
Oh, definitely. Big ones. For starters, why this specific structure? Why the U1, XSU2, XSU3 gauge groups for the forces? The model doesn't explain that, it just uses them.
And the masses. The Higgs explains how they get mass, but not why they have the specific mass values they do.
Exactly. Why is the top quark so incredibly heavy and neutrinos so light? The standard model has about 25 or 26 parameters, masses, coupling strengths, mixing angles that have to be put in by hand, measured experimentally.
That doesn't sound very fundamental.
It suggests there might be a deeper theory underneath, one that explains why these parameters have the values they do, hopefully deriving them from fewer, more fundamental principles.
And neutrinos themselves are a puzzle piece, right? Their mass.
A huge one.
Yeah.
The original standard model had massless neutrinos, but experiments, particularly with neutrinos from the sun and those created in the atmosphere by cosmic rays, showed conclusively that neutrinos do have mass, and they oscillate, they change flavor as they travel.
So an electron neutrino can turn into a muon neutrino.
Yes. This requires them to have mass, and for the flavor states to be mixtures of mass states. It's a major discovery, definitely physics beyond the original standard model, though we've incorporated neutrino masses into extensions of it.
So lots of open questions. Where do we look for answers?
We push the frontiers. Particle accelerators like the Large Hadron Collider at CERN smash particles together at incredible energies.
Looking for new particles or deviations from the standard model's predictions.
Both, exactly. By going to higher energies, we probe smaller distances and can potentially excite new, heavier particles predicted by theories beyond the standard model, like supersymmetry or extra dimensions. Or we might find that known particles behave slightly differently than predicted, hinting at new forces or principles.
The quest continues for a more complete theory.
Always. The standard model is amazingly successful, but we know it's not the ultimate description.
Well, this has been a fascinating deep dive. We've gone from the basic building blocks and forces right through to the subtle but vital roles of mesons in both holding nuclei together and enabling quarks to change identity.
It shows how interconnected everything is at the fundamental level.
Absolutely. And maybe a final thought for everyone listening. Particle physics keeps showing us that reality is, well, stranger and more dynamic than we often perceive. Just think, every time a quark changes flavor inside a decaying meson, it's like a little message from this incredibly complex quantum world happening constantly, everywhere. Remind you there's always another layer beneath, another secret the universe is waiting for us to uncover.